that concludes the official business part of the meeting. So at this point, I'd like to hand it over to our main presentation tonight, which is going to be our very own Leon, NT8B. He's going to do a presentation about antennas, portable antennas. I think it's going to be pretty fascinating. So, Leon, if you are ready to go, please feel free to take it away.
All right, I am. Thank you very much. All right, very good. Well, thank you very much, everyone, for being here this evening. I'm going to spend a few minutes talking about some experiments that I've been doing with end-fed antennas, and my intent is to use these for portable operations. So the outline for the presentation this evening is I'm going to talk a little bit about why am I interested in these antennas, and then move into a little bit of a background about half-wave antennas. As I've done this, I've learned a lot about these antennas, and they're actually fairly interesting critters and are quite useful. And there's a lot of variations on the theme, which I'll mention as we go through this. And then I'm going to give a practical example of how we use these antennas in a Parks on the Air activation. In fact, Mike Magnotti, KD4MM, and I braved the blazing cold wind yesterday and went to a park down on the Potomac and set up these antennas, and we had a really great time. We had made a lot of contacts, and I'll show you how we set up and how we used it. And then following up on the maker theme that we heard a few minutes ago, I'm going to talk about how to build these things. You can actually build one for somewhere between $5 and $10 all in. And it's really fun to do, and you'll learn a lot doing it. And then I just have a couple of closing comments as we get close to the end. So as I was looking for an antenna for this Parks on the Air work that I'm interested in doing, there was kind of a set of criteria that I set up for this. I wanted a small size antenna that I could slip into a backpack for Parks on the Air, the Summits on the Air, and special event type stations. And I also wanted something that's very easy to deploy. You know, I've been on remote sites, and I've spent more time setting up antennas than I have operating, and so I've decided no more of that. I want an antenna that's easy to put up and then easy to take down when I'm done. And then the other thing is that when you get into parks, you need to have a manageable footprint, because you can't spread out all over the place because there's other people in the park, and park rangers don't like you doing destructive things or being intrusive in the park. So I want something that's subtle and but also works. A couple of cherries on the top would be to have the antennas be multi-banded and to be able to operate without an antenna. And then, as I mentioned earlier, I want to be able to make these things myself and have them work well. So no small list of criteria, but it's interesting that the end-fed antenna seems to move me in that direction. So let's talk a little bit about half-wave antennas. A very common half-wave antenna is the antenna that we learned way back in our tech licenses and our studies for our general exam, and that is the half-wave center-fed dipole. So these are antennas that are composed of a half wavelength of wire for a frequency that you wish to operate on, and that half wavelength of wire is split in the middle, so you have two arms 1/4 wavelength long, that's fed in the center with, if you're using typical coax, you'll feed one side of the antenna with the center lead and the other side of the other arm of the dipole with the braid. And if you feed in the center, you'll find that the input impedance is right around 75 ohms. And when that's fed with a coaxial cable, the 75 ohm to 50 ohm is close enough to not cause any significant mismatch problems. And so we can usually get away with attaching a 50 ohm coax to a dipole and operate quite nicely. Thank you very much. But one of the things that we should do in this case is add a 1-to-1 current balun. And what the current balun does is it blocks common mode currents from flowing back down the outside of the coaxial cable and getting back into your shack and causing any problems. But again, we all know about this antenna, very commonly used. It works really well. Typically operates on one frequency. It's cut for one frequency, and you can make them work on the third harmonics as well. So if you have an antenna that's cut for 40 meters, you can get them to load on 15 meters. But typically, one would operate these dipoles as monobanders. So then, interestingly enough, what you can also do is you can move the point at which you feed this half wavelength of wire. And as you move away from the center, big surprise, these antennas are called off-center fed dipoles. And there are a number of different versions of these dipoles. You can see here on these slides that folks set these up so that you can have 2/10 of a wavelength on one side and 8/10 on another, 25, 75, 33, 66. So different variations are used by various operators for various reasons. The point I want to make here is that you can still operate these antennas, but as you move the feed point away from the center, the input impedance changes. So typically, the input impedance on an off-center fed dipole, where it's off-center fed in the kinds of ratios that I show here, tend to be somewhere in the neighborhood of 200 ohms. So then, in order to make the match to the 50 ohm coaxial cable, what's often done is a 4-to-1 balun is used, which allows the 50 ohm feed line to match the 200 ohm input impedance, and you're able to operate again with a fairly reasonable match and do very nicely with these things. And then one of the advantages of the off-center fed dipole is if you have one cut for 80 meters, for example, it will typically operate also, it'll tune on 40 meters, it'll tune on 20 meters, it'll tune on 10 meters, and so forth. So these antennas operate more as multi-band antennas than does a center-fed dipole. And then finally, moving the feed point to the extreme so that you have an extremely off-center fed dipole. You roll down to the end where you can feed the antenna. And it turns out that the input impedance when you feed the end of a half wavelength piece of wire, that input impedance is somewhere in the neighborhood of 2,500 to 3,000 ohms. And so, of course, that's a pretty huge mismatch. But it turns out that there's a little small counterpoise that can be used, but it turns out that it's possible to very easily, and I'll show this in a minute, to make an impedance transformer that has the ratio of 49-to-1, and that allows you, again, to get a pretty good match between the 50 ohm impedance of the coaxial cable and the input impedance of the antenna at the end of the antenna. And again, you're still operating with a half wavelength antenna. So if you cut if the half wavelength is cut for a 40 meter antenna, it turns out that these antennas will tune not only on 40 meters, but also on multiples of the band. So, and I'll show you this again in a few minutes, these antennas will tune not only on 40 meters, but also on 20, on 15, and on 10 meters. So they're very flexible antennas. It is possible to, and sometimes wise to use a 1-to-1 current balun on these antennas, but it's very important not to place if you use one of these current baluns, is not to place it at the feed point, because there is some common mode current and other currents that need to flow back into the coaxial cable. So if you prevent that from happening, the antenna won't work. The thing that's nice about the end-fed antennas is that you can be quite flexible in the installation. They can be installed horizontally. We've been using them as slopers in our portable operations, but they can also be used in a vertical implementation, and also used as an inverted L. So quite flexible in the way you can set it up, which again makes it really nice for portable operations like I'm going to describe in just a minute. And as I already mentioned, it tunes on the primary frequency. So for example, if your antenna is cut for 40 meters, it'll tune on the bands that I mentioned just a second ago. So that's a quick overview of the antenna and its rough design. I'll have more to say about the design of the antenna, but I thought it might be useful for you to see how we set these things up and to give you a sense for how well they work for us. So as I already mentioned, Mike Magnotti, KD4MM, and I did a little Parks on the Air activation yesterday, and we took a little trip down the road to Mason Neck State Park. So Parks on the Air is a national program that provides an opportunity for amateur radio operators to set up portable operations in either national parks or state parks. There is a extensive network of communication that allows you to spot yourself. And so there are folks who are interested in working parks that are activated, and then so those are called chasers. So there's a lot of chasers out there. And then there are activators who go out to the parks and they call CQ, Parks on the Air, and the chasers will make contacts with the activators, and it's all good fun for everybody. So Mike and I announced to the world through the Parks on the Air website that we were going to be at Mason Neck State Park yesterday, which is right down here, and we took a little drive down there, and this little circle is a blow-up indication of the map, so you can see we're right on the river here, and we ended up setting up a little station right here. There's a little parking lot right here, and we were able to take our gear and set it up on a picnic table, as I'll show you here in just a second. And once we got set up, we made a ton of contacts before we froze to death and came home. So the configuration for this antenna that we used yesterday at Mason Neck is the slope configuration. So basically what we did is we had, and when you set these up in a slope configuration, you need some kind of support structure. So this could be a tree, this could be a light pole, or it can be a mast, like I'll show you in just a second. And the wire runs out over the half wavelength, and then you have the 49 to 1 impedance transformer connected to the coaxial cable that ultimately goes to the radio. And again, you can use whatever support structure you want. It doesn't have to be particularly tall. I usually have been aiming for about 30 feet off the ground, and you can do that if you have a tree nearby, and if the park ranger doesn't mind you putting a line in a tree to pull up an antenna, you can use a weight, flick it up over a branch, and pull the antenna up that way. Or what I've been doing recently is using a fiberglass mast. It's a telescopic mast that I can stick in the ground and attach the antenna to and raise it up. So these fiberglass masts are readily available from places like DX Engineering and other sources. And then I came across these, they're electric fence posts that they're meant for portable, movable electric fence. I just picked these up at Tractor Supply. And you can see it's a fairly stiff plastic that has a spike and a footstep here. So you can take the electric fence post and stick it into the ground, and it will hold the mast up. So this is basically how it works. I just use some of these Night Eyes twisty ties here to attach the antenna to it, and then you pull the cap off, and you can see the segments of the mast are all collapsed inside this thing, and you just begin to pull them out, and you can extend the mast up to its full length, and voila, you've got a nice antenna mast. This particular mast is a 10-meter mast, so it gets the end of the antenna up about 30 feet off the ground. And the other thing you can do is, if I can back up here, whoops, let's go back this way. This by itself will actually hold the mast up as long as you don't pull too much on the end of the antenna wire when you get it up, when you raise it up. Or you can also take a couple of pieces of string and some stakes and provide a little tripod action with a couple of little guy ropes. Or as we did in the park yesterday, you can snuggle up to a fence post, for example. And I have one of these great big twisty ties. I put the electric fence post right up next to the fence post that was at the park, and put this big twisty tie around it, and it held this mast very firmly in place, and off we went. So yeah, I attached the antenna to the mast with this little thing called a bongo tie, and then you can raise the mast right up, and here it is up to its 30-foot extent. You can't really see the wire here, but I have a 30-meter a piece of wire that's cut for 30 meters that's running down in this direction here. And then, again, this is the homebrew aspect of this antenna. What I've done is I've made a wire winder that I've mounted the 49 to 1 transformer here. I've got an antenna connection with a wing nut here so that I can use whatever cut length of wire that I want. And then I have an SO239 connector that I attach the feed line to, and that's what, that's what goes, getting ahead of myself, and that's what goes back to the radio station. So this is the basic setup of the 49-to-1 transformer where the antenna attaches, feed line attaches here and goes back to the radio station. And this is what it looks like. I use a second one of these electric fence posts. Again, you can see it's just stuck into the ground and attached to the fence post with one of these little releasable ties. This is the transformer. The antenna feed line attaches here and goes off in this direction, and this is what goes to the radio station. So Mike, at the same time, set up his antenna, and he found another fence post, and he bungee corded and twisty tied his mast to a post that was downrange of mine. On this site where we were at, my antenna that I just showed you is, you see this little pathway here, my antenna is back in the trees kind of around the corner here. So he came up along the river. This is where he put his mast, and this is a long distance shot of his mast up in the air. You can see the top of the antenna is here. You can just barely make out where the wire goes, and the wire comes down to again, another one of those transformers, and so he just looped the transformer over the edge of the fence, and this is the feed line that ran back to the station. And then here's the station. We found here's where we set up our station. This is a little picnic table that was on the site. This is Mike's operation here, and then this is my laptop, and my radio is just off to the side here. So Mike was operating to the right side of the screen, and I was operating to the left side. So that's how we were set up, and it worked really well. Now you might be asking, how well do these antennas work, and how do they tune up? This is a plot of that shows both the standing wave ratio, the SWR, and the return loss that is measured across the frequency range that I tested on this antenna. So what this graph shows along the x-axis here is the frequency that is measured by the antenna analyzer. It starts down here at 1 megahertz, goes to 7, 13, 19, and 25. So this basically covers all of the HF bands. And on the y-axis here, we show the SWR. SWR equal to 1 and SWR equal to 2 is demarcated by these dotted lines. And then the vertical lines here show the different bands. So this is 40 meters here. This is the 20-meter band, 15-meter band, and 10-meter band. And what you can see here is that, and then in this case, the wire that I'm measuring, the antenna wire, is cut for 40 meters. So you can see that the SWR for the 40-meter band is less than 2 across the band. It's less than 2 at 20 for most of 15 meters and for a pretty good chunk of the 10-meter band. And none of these are, if you want to operate on any of these bands, if you do have an antenna tuner either in your radio that you brought with you, it can clean things up pretty nicely, and so the antenna will tune up and work pretty well for you. As I mentioned, if you're in a tight space, you can use a shorter antenna. So it turned out that where I had chosen yesterday to set up, the 40-meter antenna was getting tangled up in the trees because of all the wind, and it was tough to find a place to fit the full length of the antenna. So I have wires that are cut for 40 meters, for 30 meters, and 20 meters. So I put up the 30-meter antenna, and then I ran an SWR check on the antenna. And again, you can see for a good, for all the 10-meter band, the SWR was less than 2 to 1 across the whole band. So this antenna wire is a little bit short, but still very usable on 30 meters. So they work quite well. And then, the proof of the pudding is in the operation. So Mike and I got there to the park at about 10:15 yesterday, and we scoped the site, walked around, chose the spot where we were going to set up, and we were able to get that done by 11. So I figured 45 minutes to check out the site, figure out where we're going to do it, put the masts up, wire up the antennas, get the radios ready to go in 45 minutes is pretty good. And then we sat down and started to operate, and Mike had the greatest success with his station on sideband, and he was hauling in the QSOs like shooting fish in a barrel. It was really fun. And then I took a turn on his radio and made enough to activate the park for myself. And we had contacts as far west as Alberta, Canada, and Calgary, and Las Vegas, Nevada, and south of Puerto Rico, and many of the states in between, and even had a couple of little mini pile-ups. And the signal reports we were getting back on the antennas were 5/8s, 5/9s, and more than that. So got great signal reports. People were hearing us, and we were hearing them. And then, like I said, the wind was blowing like crazy across the water, and it got so cold I could hardly type on the typewriter anymore to log the call. So we threw in the towel about noon and pulled the antennas down, and we were back on the road heading toward our warm homes at about 12:30. So the weather for us was the biggest problem of the day. So the bottom line is that the antennas worked for us really well, and we had a lot of fun on just even a short little activation. So that's the story on the antenna. It works well. It meets a lot of the design criteria that I was interested in. And in case you might be interested, and again, building on the maker theme, I thought I would spend the next few minutes talking about how I built these things. And they're really easy to build. And if you're interested in one, you can build one for less than $10, and it should work really well for you. So the way these things are set up, as I mentioned, is that what's really key is the 49-to-1 transformer. So the primary of the transformer is connected ultimately across the center of the coaxial cable and the braid on the outside, and then the antenna itself is connected to the secondary of the transformer. It's useful to put a capacitor that is a value of 100 picofarads, high voltage capacitor between the two sides of the transformer, which helps with tuning. If you want to use it as a multiple band antenna, it helps with tuning at the higher frequencies. And then some people use a little short counterpoise that is cut to approximately 0.05 wavelengths on the lowest frequency that you intend to use. But basically, this is it. This is the full design of the system, and so it's really quite straightforward. You heard a little bit earlier from Dean that I'm interested in 3D printing, and so I whizzed up a wire holder that will hold both the transformer and the connector that I'm interested in, and I built these things for both BNC connectors because my QRP radios have BNC connectors, and then the ICOM 7300 I was using yesterday has PL259, so I have an SO239 setup as well. And so you need some kind of a holder or a carrier for the transformer that you build. I like the winder because ultimately I want to just be able to have this winder dropped in my bag to be able to pull it out, unwind it, and have it all be in one piece. And you also need some wire here to wind the transformer. Here's the capacitor that I mentioned, and there's some screws that you need to attach the connectors, but pretty much that's it. So it's really simple to make these things. This is the 49-to-1 transformer. It's really easy to make, and so here it is. You need a ferrite core. These are readily available from Mauser. They cost $1.43 each. And Mauser will sell you one, if you can imagine. It costs you $7 to have it shipped to you, but you can buy one if you want. I don't recommend buying just one, but anyway, you can get them readily from them. And then there's the wire that you need to wind these things. In this case, I've been using 18-gauge enamel-coated wire. And the way you do this, and I put these numbers in here so you can get this presentation, and you can do this in a fairly cookbook fashion. But you cut two segments of this wire. One is a little over 1 meter long, and the other one is about 1/3 of a meter long. And what I do is I twist the two segments together for 180 millimeters, and then start winding the transformer. So, and the way this works, it's really quite simple. It's you need a 7-to-1 ratio of turns, primary to secondary. Actually, these are secondary to primary to make the transformer. in order to know what the transformer ratio is, you look at the turns ratio and square the numbers. So anything that is in a 7-to-1 ratio will end up being a 49-to-1 transformer. So in the example that in the antenna that we used yesterday, the transformer I made has 21 secondary turns and 3 primary turns. You know, the ratio here again is 7-to-1, no big surprise, which is the 49-to-1 transformer. Or you can do 14 secondary turns and 2 primary turns. Again, it's very easy. You just wind the twisted pair around the toroid ring through the center 3 times if you do 21-to-3 setup. And then you reserve the ends for connections to the connector. And again, I've used SO239s or BNCs. You could use other connectors if you want, of course. You wind the single wire through the center. After you do the 3 turns, you wind the single wire through the center 7 more turns. So you can see the 3 turns of the twisted, the bifilar turns of the transformer here. Hang on a second. 7 times around more here. And then what you do is, if you want, you can cross over the center to the other side and start the windings around the other way. And the reason you do this is that when you get done winding, this wire, which attaches to the antenna, is on the side of the toroid that you want it to be. And so you just pass it through and wind it around till you have a total of 21 turns. And that's it. That's the transformer done. Really easy. And then I used some crimp-on connectors. I use this one for the antenna connector, and this one goes on the ground. And then this, you can see I scraped off the enamel here, and that's where I solder it into the connector, either the BNC or the SO239. And then again, it mounts into this mount that I've made. You can use something like this that I've 3D printed, or you can do it in a box. So a project box works just as well. And here you can see I've installed the 100 picofarad high voltage, it's 10 kilovolt capacitor. And now it's ready to go. This is it. It works. And then,
Leon, can I quick question?
Yeah, sure, Mike. Go ahead.
How do you attach the toroid, or how do you make it stay in there and not fall out?
So I didn't show it on this one. Well, first of all, I've made the fit tight enough so that it doesn't come out, Mike. But right here, I've designed into the winder. There's a little opening here, and inside there's an opening. There's a little opening here you can see, and there's another one in there. And I just use a zip tie to fasten it down if I want to really make sure that it stays. But I have to say that with this connection here and this connection here, it stays in pretty much by itself. Okay.
Okay, thanks.
So let me just finish this, and then I'll break for questions. So, and actually, I'm getting pretty close to the end of the presentation anyway. So, and again, if anybody in the group here is interested, what I've done is I've got 2 little cookbooks here. One is for the SO239 based end-fed half wave, and I've listed all the sources for the toroids from Mauser, the connectors from the RF connection, and then I use metric hardware now, primarily because of all the 3D printer work that I've been doing, wire connectors and so forth. So if you want to make one of these things, you can find all that you need right here. I've got a link to where I got the capacitors from eBay. So it's all here if you want to do it. And then I have the same thing here for the BNC based system. So as we do, I'll give the presentation to be posted on the Vienna Wireless website, and you can find this for your future reference going forward. Now, one of the other things that I've done is I've also experimented with a system that uses bigger toroids and slightly larger diameter enameled wire that's suitable for operation at higher power. So the smaller one here that I showed is suitable. It worked really well for us on sideband running 100 watts. We didn't have any problems. I think we'd probably be pushing 100 watts if we were running CW. So there are some designs for these things that you can use for running a little bit higher power. So in this particular example, these are still 43 mixed toroids, But in this particular design, there are two toroids here. So you can see the top one. There's a second one lying just underneath it. And then I wound this transformer with two of the twisted pairs, and then a total of 14 winds on the transformer. So again, you have the 7-to-1 ratio, but not quite so many turns. And this will work a little bit better with higher power. I don't have any problems operating 100 watts CW with this particular setup. And again, it's the same design. The antenna goes here. We've got the 100 picofarad capacitor, and in this case, it's an SO239 connector. So, and we used this whenever we went down to Cobb Island. So this was the end-fed antenna that we used when we were down there. And again, it worked very, very well for that particular event. Just a few kind of ending comments that I have here about the antenna. I mentioned a little bit earlier that some folks advise using a common mode choke, 1-to-1 balun on these antennas. I've found that you really don't need it if you're operating QRP, but if you run higher power, it may be needed to block some common mode current that could dance down the feed line and cause you some problems. When we were out yesterday, we were running with fairly long feed lines, and we weren't troubled with any common mode current getting back into the radios. And the other thing that's really important with these is that you can't put the choke right at the feed point. It kills the antenna. So you need to let there needs to be some space for currents to dance around down the feed line for some distance, and then if you leave at least a 0.05 lambda or more, you can put a common mode choke in, and all is good with the world. And then for comparison, I just wanted to mention that there are a large number of commercial end-fed half-wave antennas that are available, and they're available for a price. So I did a little bit of a search today just to find some examples, and there's a Vibraplex makes an antenna called PAR end-feds. They start at about $160. Radio Waves makes one starting at, they several models again starting at about $100. Pactena has a real nice portable end-fed half-wave that is $89.95. MFJ has one that's $70, and they go up from there. And then QRP guys has a kit that runs $30, but it's, when they say QRP, they mean QRP. So it's meant for 5 watts and left. It has a very small toroid and wouldn't be suitable for running any kind of power if you're operating remotely, for example, with a 7300 or like Mike was using yesterday with his Yaesu radio. I'll also mention something that was confusing to me as I was first getting into building these things. There is another type of antenna that is known as a random length end-fed antenna as opposed to a half-wave end-fed antenna. And the random wavelength antennas, they're not the same. It's a different design. So whereas with the end-fed half-wave, the antenna wire itself is cut for half-wave, in the random length antennas, the wires are cut so they are not any resonant wavelength. And there is a table available on the Balun Designs website. It's a really nice table, and there's other sources on the internet. But if you go to balundesigns.com and look under random length end-fed antennas, that section of that website, the owner of the website has a nice table that describes defines the lengths of the wires that can be used with these antennas. So they're cut to be non-resonant, and you use a 9-to-1 transformer with that particular design. And it turns out that an antenna tuner is required with these antennas. So you can get them to work, but you need to have an antenna tuner either built into the radio or one alongside with you. And as I've read about these antennas, they do work, but folks call them compromise antennas. And if you have a chance and can put up with the extra length of the half wavelength wire, the performance of the end-fed half-wave, the efficiency of the end-fed half-wave antenna is better than the random length end-fed antennas. So I just wanted to mention that just in case there was any confusion. So what's next for me with these things? I want to do more OTA activations. There's POTA, IOTA, summits on the air. I'm looking forward to taking my radio out. I want to get out. I want to get portable. I want to go out walking, get into some of the parks, and do some of these things. So yesterday's event was a lot of fun, and I want to do a lot more of this going forward. So I'm going to play around with these antennas, and this particular setup seems to work for me for pretty well. And then one of the things that I don't want to do so much is if I want to change bands, I like to go from 40 meters to 30 meters. I have to pull the whole thing down and change the wire to get a shorter wire. And so what I want to do is begin to experiment with either some form of linked antenna. So the example here is you could see that the way this is put together, you have the full length of the antenna. But what you can do is you can put a little breakable link in the wire so that if you have an antenna that's cut for, say, 40 meters, you can put one of these links at the point where the antenna would be resonant at 30 meters. And when you want to operate on 30 meters, you just unplug the plug here so that, in effect, you have a wire that's equivalent to the length of a 30-meter half wave as opposed to the 40-meter half wave. So it's easier to pull it down, unplug it, and raise it back up than it is to change the whole wire. So this is a halfway step to having some flexibility. And then there are some designs out there where folks have designed some lightweight inductor capacitor traps so that these behave as electrical endpoints in the wire, and they can be used to electrically shorten a piece of wire so that you can use it on multiple frequencies. So haven't done any of this yet, but it's something that I'm interested in pursuing as I go forward. So there's a ton of references out there that describe how these things work and how to build them. One reference that I found that I think is really great is it's a paper that's titled "The End-Fed Half-Wave Antenna," big surprise, by a gentleman, Steve Dick, K1RF. I provided the link here for you, and if you're interested in these antennas, I really recommend that you download this because he's got all kinds of information on different sizes of toroids to use, wires to use, how they work, things to avoid, things to do whenever you build them. It's really a very good paper. And there's a ton of YouTube videos out there. There's a gentleman named Steve Ellington, N4LQ, who he has a channel, and he's described a lot of the work that he's done. He's less interested in portable operation than he is setting these antennas up for home use. You can use them for home use, and you can cut them for any half wave. So he has a design that is cut for 80 meters, and he adds a capacitor and a little inductor in the system that helps it tune across 80, 40, 20, 10, and so forth, and it makes quite a flexible operation or antenna that you can use at home. And then another guy who I just think is kind of funny is Gilles is his name. He's a Frenchman who calls himself the radio prepper, and he's done a number of videos on where he talks about both end-fed half waves and random length antennas, and shows how he puts these together and how he's used them in the field. And I found his videos useful as well as being entertaining. And again, I provided some links here. And there's a lot of sources. People use these antennas pretty widely, experiment with them. They're available on YouTube and on the World Wide Web. So lots of stuff out there if you want to know more.
I was just going to say thank you very much, Leon. This is great.
Okay,
this is really cool.
Yeah, I've had a lot of fun with this, and I'll look forward to keeping you posted on. We'll see how it goes. So the experimentation shall continue. So thanks for your attention, and back to you, Andrew.
All righty. Well, thank you, Leon. That was excellent, and I might be calling you for one of those binders at some point.
Let me know.
Yeah, they're pretty cool.